Hi, everyone. Let's finish our discussion about gases. So last time we talked about gas laws. We saw Dalton's law and ideal gas law. So let's finish it up with Dalton's law. Dalton's law of partial pressure. This one's pretty straightforward. It makes a lot of sense. It might be one of the more important ones. So Dalton's law simply says that if you have a mixture, like in this last container over here, of two different molecules, different gases, you can think of that being like the sum of separate containers of those gases. So what you can do is, if you count up the little balls here inside each container, that represents the number of molecules of the gas. The idea, you have so many molecules of gas number one here, so many molecules of gas number two, mix them together in the same size volume, and the pressure is going to be the sum of the two pressures when the gases are separate. And what really happens, and so that's pretty straightforward, right? It's kind of like, well, that makes sense. If you take more gas, if you take some gas, add more gas to it, even if it's not the same chemical that makes up that gas, you mix them together, the pressure is going to increase. But really, the bottom line is now if you have a mixture of gases, you can pretend it's a pure gas and use PV equals nRT or any of the other gas laws, and you can make some predictions about that mixture of gases. Also, you can break it down and say, well, let's add more molecules of gas number one, and then you can calculate based on how much gas you add, what the pressure is going to be as if it was separate. And it just allows you to do a few tricks. And I'll show you those tricks in just a second. For now, I just need you to know that this is Dalton's law. And it simply just says down here that the total pressure of the mixture is equal to the sum of pressures of the individual gases. So gas number one, what's its pressure? Add it to gas number two's pressure, and then those sum or add up to the total. And of course, with every new idea comes a new term. So if we're talking about, hey, in this mixture, there's gas one and two, you talk about, well, what is the pressure due solely to molecule number two, gas number two? And the term for that is, well, what is the partial pressure of gas number two? So a partial pressure is just the pressure of one component of a gas, of a mixture of gases. Air is a mixture. So we can talk about right here in the room, in your room. Take a deep breath. What are we inhaling? Well, a majority of it is actually nitrogen gas. And the next major component of air is oxygen. And that's the one we require. But air is not just pure oxygen. Nope. It's a mixture of argon. There's some humidity in the air, water vapor, and some carbon dioxide. Right? Just exhaled some, and you go outside, and plants need carbon dioxide. That's what they take in. So the atmosphere naturally has these five gases, and there are others. Of course, you know, pollutants, but there's other molecules out there that are in smaller amounts. But these are the five major components of air. If you're curious, I believe the units here are in kilopascals. Not on the exam, but I just thought that's interesting. And they got little pressure valves on these represent that, hey, the partial pressure of nitrogen gas in air is 78.1 kilopascals. Air at atmospheric pressure is 101.3 kilopascals. Anyways, what's the partial pressure of oxygen? 20.9 kilopascals is the answer. Most of the time, though, at least on my exams, we'll be working with atmospheres, maybe millimeters of mercury or torr. Okay, here's a sample problem from an exam. Let's say there's a scuba tank, and it already contains 2 atmospheres of nitrogen gas and 1 atmosphere of oxygen gas. And then someone just adds in some carbon dioxide and then measures the total volume, I'm sorry, not volume, the total pressure in that tank, and it's 4.6. And then the question is, well, what's the partial pressure of carbon dioxide? Okay, so on the exam, if you saw this, first thing I would realize if I was a student is that it's a mixture. Nitrogen, oxygen, carbon dioxide, all being put into the scuba tank. And I don't know why carbon dioxide is being added to a scuba tank, but anyways, it's a made up problem. Anyways, it's a mixture. And so that hopefully would remind everyone, including myself, it's Dalton's Law. So Dalton's Law says add up the individual pressures. So what's the pressure due to the nitrogen, plus the pressure due to oxygen, plus the pressure of carbon dioxide? That's got to equal the total. There you go. I know it's pretty straightforward. Just need you to memorize it. And then when it says the partial pressure, this is the number that we want. So what are the numbers that we know? Well, we're told there's 1 atmosphere of nitrogen. Sorry, that's a 2. 2 atmospheres of nitrogen, 1 atmosphere of oxygen. Don't know this. You can change it to X. If you want to use the variable X here, you can. I'm going to leave it in the variable partial pressure of carbon dioxide. The total is 4.6 atmospheres. This sums up to 3. So let's subtract 3 from both sides, 3.0, and you get 1.6. And that is the partial pressure. If I make a lowercase, so it looks like cobalt, but it's carbon dioxide. It's 1.6 atmospheres. Cool, Dalton's Law, pretty straightforward. Percentage of the gas. Well, what percentage is carbon dioxide? Well, remember a percentage is the part divided by the whole. And then you want to make a percentage, so multiply by 100%. So what's the part? Well, the partial pressure. That's the part that's carbon dioxide. That's 1.6. Whoops. 1.6 atmospheres. The whole, or the total, is 4.6 atmospheres. And then we want to change it to a percentage, so multiply by 100. And so if you get your calculator out, 1.6, where did I put it? Divided by 4.6 is about 0.3478 times 100. Let's use 2 significant figures. I got 35%. That's 35% carbon dioxide in that scuba tank. Cool. All right, I think that's Dalton's Law. If you take more chemistry, you can go farther with this. What's really cool, just as a preview, let's say you have that scuba tank, or let's just look at this container. You can measure, and maybe that's what this ruler is doing here, measure the size of the tank and then calculate the volume. And the volume's not changing. The pressure is the thing that is changing, but you're measuring that so you know it. And then R is a conversion factor, the universal gas constant, 0.08206, I think is a number. We can look that up. And then temperature, well, you have to measure that. Make sure it's in Kelvin. Anyways, if you know the volume of your container and the temperature, and you measure your pressure, you then can calculate moles. And if you know the number of moles, you can use that to calculate some calculations. You can calculate some calculations. You can do some calculations about chemical reactions. You can do some stoichiometry. So if you want to use a gas as a reagent, well, get your sealed container, pressurize it with the gas you want, measure the temperature, and using PV equals nRT, you can then calculate the number of moles of that gas that you have. And if you have a mixture, not a big deal. Take your container, start with a vacuum, add some, maybe the nitrogen gas to a certain pressure, then add the oxygen gas, get that pressure, and then all you're doing is measuring the final pressure. And just, if it was empty, you put in the nitrogen, the pressure you measure, the total pressure, all due to nitrogen. And then you remember what that pressure was as you add more oxygen, and then the increase in pressure tells you the partial pressure of oxygen. And then if oxygen's a reagent, for example, you then have the partial pressure, you know your volume, your temperature, you then can calculate the number of moles of oxygen. Cool. Okay, the other thing we're going to cover in this video is, oh no, one more idea about Dalton's Law. I mentioned the scuba diver, so there's a picture of someone's underneath the sea scuba diving. Cool. Here's some pressure gauges down here. Good idea to keep an eye on how much air is left in the tank. Dalton's Law is helpful for a safe dive because as you descend deeper and deeper, the pressure, the water pressure, will actually pressurize the air. So as you inhale, I know this is pressurized, it has to be forced into your lungs under the deep sea or underneath water, because the water's pressure, you actually are making the air more dense, right? So here is a volume of air. As you descend this cup of air, let's say it's an inverted beaker maybe, the water pressure is going to compress that gas as you descend deeper and deeper under greater volume, greater pressure of water. And then as you inhale, you're going to still inhale the same volume, you know, still fill your lungs as you inhale with the scuba tank, but the air is more dense. So every breath you inhale is going to contain more oxygen. So that's the idea. So if you inhale this much volume, and then up here you take half of that, and here you take this much, you can see that there's more molecules of gas at lower depths because the air has been compressed. Now that's a problem for deep sea divers if you just have a scuba tank filled with pure air. Sure, pure air is fine for you and I at normal pressures, 1 atmosphere, but every breath at deep levels is you're gonna actually take in more oxygen molecules. So there's something called oxygen toxicity. So it can be very hazardous. So what you need to do is, if you plan to spend time deep in the water, is change your ratio of oxygen and nitrogen in your tanks. Or you can add helium. Helium's inert, and it's an inert gas, a noble gas, it doesn't react. Maybe make your voice sound a little squeaky, but who's talking when you're scuba diving? You're not going to matter. It's not going to matter. So that's what you can do. Even though the air becomes more dense, you can substitute the oxygen gas with helium. So at deep depths, as you inhale the more dense air, most of it will be helium and the correct amount of oxygen. If you fill the tank correctly, you can see all these valves and the scuba tanks here being filled by hopefully a trained professional there, can get the ratios correct. And it's just a matter of watching your pressures using Dalton's Law. So as you monitor the pressure, you can calculate how many moles of each gas is going into that scuba tank. Cool. All right, new topic. Vapor pressure and boiling. So here's the idea. If I go and spill some water on the floor and I'm lazy and I don't mop it up, if I come back the next day, the water will be gone. But did it boil? No, not if it's sitting on the floor. The floor never got to 100 degrees Celsius, the boiling point of water, but the water's gone because it evaporated. And so that's always happening, just about at any temperature where you have a liquid, and not just for water, right? Other liquids too. Alcohol will evaporate, gasoline will evaporate. You can even think about cooking oil. If you get hot enough, it can evaporate. Yeah, so all liquids can evaporate. And what happens when liquids evaporate? Well, they turn into a gas. And if you have a gas, you could calculate and measure the quantities, the pressure, the volume, the number of moles, and the temperature. And then that gas that's being created by evaporation has a pressure to it. So there's something called vapor pressure, where if you just have a pure liquid Actually, it doesn't have to be pure. It could be a mixture, and you could use Dalton's law to talk about the mixture of gases. But let's just talk about one pure liquid. Maybe it's water. So at room temperature, a small quantity of the water will evaporate and create water vapor. And if you seal it up, there'll be water vapor inside this container. And now that you have a water vapor, that's a gas. It has a partial pressure. And what we'll say is, hey, well, what is the pressure due to that vapor that formed by evaporation? Or simply, what is the vapor pressure? Okay, so vapor pressure is just the pressure due to the vapor, the gas that came off of the liquid by evaporation. Technically, we have to talk about equilibrium. So we put the stopper on, right? Because the gas could escape and then more liquid would evaporate and keep on evaporating if there was no stopper until the entire flask was empty. But let's maintain equilibrium. Let's stopper it up. And so evaporation takes place very quickly at the beginning so that the vapor will fill up the container, but there's still air in there. At some point, there'll be enough of the liquid turning into gas, and these little gas molecules are bouncing around in the container, and sometimes they collide and go back into the liquid. And sometimes the liquid then would evaporate, some of the molecules in here would collide with enough force to kick them out of the liquid state and back into the gas stage. And there's an equilibrium that's reached, where at some point, the number of liquid molecules changing to a gas equals the number of gas molecules changing back to a liquid. And then the vapor pressure, or the amount of gas caused by evaporation, will remain constant. It'll be at equilibrium. Cool. Okay, so now what we want to do is make a clear distinction between evaporation and boiling, right? So I spilled the water on the floor, come back the next day, the floor is dry. It's incorrect to say the water boiled away and never reached 100 degrees. It evaporated. Yeah, just through evaporation, right? That's what happens outside on the lakes and the streams. Sunlight warms up the air, warms up the earth, warms up the water, and some of the water evaporates, goes up in the sky and forms clouds. Okay, so the water doesn't boil off of the lakes and ocean and stuff like that. So what is boiling then? Well, from a chemistry or physics point of view, boiling is the temperature at which the vapor pressure equals the atmospheric pressure. Okay, what are we talking about here? So let's pull the stopper off of this bottle and just allow this liquid to start evaporating. And the amount of vapor that's created has its own pressure. And at room temperature for water, that's not very much vapor. But if you heat up the water, so a lot of it is evaporating, you're gonna get a lot more gas, a lot more water vapor. And if you look, hey, how much pressure is all this water vapor creating? Well, at some point at 100 degrees C, there'll be enough gas coming out through evaporation that all that gas has the same pressure as the atmosphere. And that defines the boiling point, where evaporation happens so fast that the gas you create equals the external pressure, equals the atmospheric pressure. So that's what this diagram is representing here. So room temperature or warm water, whatever, it's evaporating, water molecules coming out, becoming water vapor, adding to humidity. It's steam, it's liquid, it's not liquid, it's gaseous water vapor. And if you heat this up and get it so hot that even within the liquid, the evaporation takes place so fast, the liquid water molecules bounce around and they push away from each other and jump until they're unstuck from all their neighbors. That defines a gas, right? Gas molecules are moving so fast that they can't stick to their neighbors. Liquid molecules are moving fast, but they remain stuck to their neighbors, or as they slide around, they're still sticking to their neighbors. That's a liquid. So if you have liquid water, it's getting hotter and hotter. The liquid water molecules are sliding past each other faster and faster, and they start colliding faster and faster until they can bounce off of each other within the liquid down in here. And enough of these water molecules move so fast, they can push the liquid aside they can evaporate, become gas so quickly, they can actually create an air bubble, a steam bubble, really not an air bubble. This gas is full of water vapor. It pushed all the water, the vapor pressure from the gas can push the liquid aside and make a bubble. And that defines the boiling point. How hot does the water have to be so it can evaporate so quickly that within the liquid, it can turn into a gas and start bubbling, start boiling? That is the boiling point. And so it depends on how hard the atmosphere is pushing down. So at room temperature, I shouldn't say room temperature because you gotta get this liquid water hot enough to boil. But at sea level, the external pressure is 1 atmosphere. But if you climb up to Mount Everest, you're climbing up in the mountains, there's a lot of the atmosphere below you if you're high up in the mountains. So above you is all that is air above you that's contributing to the air pressure at the top of Mount Everest. There's going to be less air pressure. And if there's less pressure, if you take a pot of water at the top of Mount Everest, start boiling it on the campfire, if you measure the water, it actually only measures 71 degrees and it'll be bubbling as it boils. Why is it bubbling not at 100 degrees, but 71? There's less pressure. You heat up the water, the liquid water molecules move faster and faster until it's 71 degrees. Now they can evaporate fast enough to push the liquid aside to make an air bubble, not an air bubble, a steam bubble, because the air pressure is pushing down the liquid water with less force. There's less atmospheric pressure. It's been measured to be 0.32 atmospheres. And so water boils at a lower temperature at higher elevations. That's true here. If you live in Colorado, you're gonna have to adjust your cooking recipes. If you live up in higher elevations, maybe even Sierra Nevadas, near Reno, wherever. So I found this on the internet. It's an adjustment guide for cooking cakes, quick breads, and muffins. And if you look at this from a chemistry point of view, we can start to make some sense. So let's look down here about why we have to add more liquid. So I don't know what we're making the muffins with. Maybe add some water. What else would you add? I don't know. There's a little milk in there, some liquid. But for each cup of liquid, they recommend that between 3,500 and 6,500 feet, add another 1 to 2 tablespoons. At even higher elevations, you need to add 3 to 4 tablespoons of more liquid. Why? Well, at high altitudes, there's less pressure. So liquids can evaporate more quickly, right? The vapor pressure is higher at a given temperature. So when you put the muffin dough into the oven, you heat it at what, 350, 325, whatever, for 20 minutes, however long it takes to cook a muffin, the water in the dough is going to evaporate under that heat. And at high elevations, there's less atmospheric pressure to keep it down as a liquid. The liquid's going to evaporate faster and dry out the muffin. So add more water so that there's more water to evaporate. So at the end of the cooking time, it should still be moist, like you would expect at sea level. How about this top item? For each teaspoon of baking powder, you want to decrease it as you go up in elevation. So use less baking powder. Well, why is that? Well, quick breads, these cakes and muffins, they're not yeast-based. They're based on baking powder, baking soda. These compounds that when you heat them up, they release carbon dioxide. They make a gas, right? So as you heat up baking powder, it releases carbon dioxide, little bubbles, that will expand the dough and make it rise. So you get a nice fluffy muffin from the baking powder being heated, generating carbon dioxide and expanding the dough. Well, higher elevations, there's less pressure. So the gas that's created within the dough is going to be able to expand higher, expand more, because there's less pressure resisting that expansion. So unless you want the muffin, expanding clean out of the container, if you don't want it too airy, you need to decrease the amount of baking powder so that the muffin's the same size at high elevation as if it was at sea level. Cool. We'll have to talk to a chef about why sugars decrease and flours increase. I'm not certain about that. We've got a couple ideas, but it's all speculation. Let's see, what else can we do here? Let's boil water at room temperature. So here's the idea. At sea level, you need to heat up this water so the water molecules move so fast they can push against a whole atmosphere of water and get out as bubbles, steam bubbles. But if you take the same liquid water to the top of Mount Everest, now you don't have to heat it as hot, only 71 degrees, because there's less pressure. And now as the water evaporates, turns from liquid to gas, it can create these steam bubbles of water vapor at 71 degrees, and that's enough to resist the pressure. Well, what if we want to lower that to 25 degrees, room temperature? We need to remove the pressure even more. So let's do that. I found a couple of YouTube videos. One I posted on Canvas, and the other one I have right here. I'll switch over here. I'm hoping that's working, but let me double check. Screen share it one more time. So what do we have here? So we got some kids in the background. I'm sure it's a fan, parents are setting this up. But you can see in the middle of the screen, there's a plastic cup filled with water. And then there's a glass bell jar, I think it's called. It's a heavy, thick-walled piece of glass. And the bottom is open. And it's put on this rubber plate to make a seal. And then in the background, right over here, you see the label and this black instrument. That's a vacuum pump. I imagine there's a hose at the top of this jar that's just going to start sucking the air out of the container. And then in the background, I think you hear one of the kids reading the pressure gauge. So the idea is that normal atmospheric pressure is about 30 inches of mercury. And the pressure gauge is measuring inches of mercury. And he's counting it down to how much vacuum pressure is released. When it gets close to 30, that means there's no air in here. But before that, it's really low pressure, and this will start boiling. So yeah, this is room temperature. If you pick that up, it would still be at room temperature. Actually, it'll start getting colder because as water evaporates, the water molecules that are moving the fastest are leaving, and the water molecules that are staying behind actually are moving slower. And if you remember from the kinetic molecular theory of gases, temperature, or rather the kinetic energy of molecules, is proportional to temperature. So hotter temperatures, molecules move faster on average. So here, if the fast-moving molecules leave, the slower ones are behind. Slower molecules have less temperature, a lower temperature. The cup of water is actually getting colder as it boils away. It is boiling, but at room temperature. That's kind of cool. Here, one thing I want to point out, let's rewind it a little bit to where it just begins to boil. Okay, that's not a bad shot. Do you see where the bubbles are? They're not at the bottom, right? So if you had a pot of water, the heat source is at the bottom. That's where it's hottest. That's where the water molecules move the fastest, can create the steam bubbles. The bubbles start at the bottom and then move their way up. But here, you don't have a heat source at the bottom. Instead, the whole thing is under reduced pressure. The water molecules at the surface are the ones closest to getting out. And so the bubbles, the evaporation is happening at the surface, and that's where the bubbles are forming, the top part of the cup of water. That's the bubbles at the bottom, though, I noticed, but most of it's at the top. Hey, that's enough for now. I'll see you in the next video.